Everything I told you last time, you can summarize in these two equations. So remember what we did. We said, let's take, for the simplest case that we can possibly imagine, namely a particle moving in one dimension along the x-axis with a constant acceleration a. What is the fate of this particle? And the answer was, at any time t, the location of the particle is given by this formula. You can easily check by taking two derivatives that this particle does have the acceleration a. So what are these two other numbers, x0 and v0, or x0 and v0? I think we know now what they mean. They tell you the initial location and initial velocity of the object. For example, suppose you use vertical motion and use y instead of x, and a would be g or minus g. That's a particle falling down under the effect of gravity. If all you know is the particle is falling under the effect of gravity, that's not enough to say where the particle is, right? Suppose we all go to a tall building, start throwing things at various times with various speeds. We are all throwing objects whose acceleration is minus g. But the objects are at different locations at a given time. That's because they could have been released from different heights with different initial velocities. Therefore, it's not simply enough to say what the acceleration is. You have to give these two numbers. Then, once you got those two numbers, they're no longer free parameters. They're concrete numbers, like maybe 5 and 9. Then, for any time t, you plug in the time t, and you'll get the location. If you took the derivative of this, you will get the velocity at time t to be v0 plus at. Again, you shouldn't memorize the formula. I hope you know why it makes sense, right? You want to know how fast the guy is moving. This is the starting speed. That's the rate at which it is gaining velocity, and that's how long it's been gaining it, so you add the two. This also means the following. It is true that if you give me the time, I can tell you the velocity. But conversely, if I knew the velocity of this object, I also know what time it is, provided I knew the initial velocity. Therefore, mathematically, at a given time t, we can trade t for v and put it into this formula, banish t everywhere. By doing it, I got this formula. This is a matter of simple algebra of taking this and putting it here. But I showed you in the end how you can use calculus to derive that. And I got the feeling when I was talking to some of you guys that maybe you should brush up on your calculus. You have done it before, but when you say I know calculus, sometimes it means you know it. Sometimes it means you know some fellow who does, or you met somebody who knows. That's not good enough. You really have to know calculus. And this is a constant problem. It's nothing to do with you guys. It is just that you have done it at various times. It's a problem we have dealt with in the physics department year after year. And one solution for that is to get a copy of a textbook I wrote called Basic Training in Mathematics. It's a paperback, about $30, and I've given the name of the book in our class's website. If I hadn't written it, I would prescribe it, but that is a little awkward moment. You don't want to sell your own book. On the other hand, you don't have to withhold information that may be useful to the class. So I think that book will give you all the basic principles you need in calculus, of one variable, more variables, elementary complex numbers, maybe solving some problems with vectors and so on, which you're going to get into. Whether you go into physics or not is irrelevant. If you go into any science that uses mathematics, chemistry or engineering or even economics, you should find the contents of that useful. So I think it'll be in your interest to get that any way you like. You can go to Amazon or you can go to our bookstore. The bookstore has some copies, but they are really for another course. So you should look at it, then order it on your own. Okay, so I will now proceed to the actual subject matter for today. So I told you the way I'm going to teach any subject is going to start with the easiest example, and lull you into some kind of security and then slowly increase the difficulty. So what's the next difficult thing? Next difficult thing is to consider motion in higher dimensions. So how high do you want to go? Now, for most of us, we can go up to 3 dimensions because we know we live in a 3-dimensional world. Everything moves around in 3D. That will be enough for this course. In fact, I'm going to use only 2 dimensions for most of the time, because the difference between 1 dimension and 2 is very great. Between 2 and 3 and 4 and so on is not very different. There's only one occasion where it helps to go to 3 dimensions, because there are certain things you can do in 3D you cannot do in less than 3D. But that's later, so we don't have to worry about that. So we'll stop with 2. If you talk to string theorists, they will tell you there are really how many dimensions? Do you know? There are actually 10, including space and times. There are 9 spatial dimensions. That's according to string guys. So mathematicians have luckily told us how to analyze mathematics in any number of dimensions. We don't pay attention to them when they're going beyond 3, but now we know we need that. So we are going to do 2. So our picture now is going to be some particle that's traveling in the xy plane. So the guy is just moving around like this. This is not an x versus time plot or y versus time. This is the actual motion of the particle. And if you say, where is time? Well, one way to mark time is to imagine it carries a clock as it moves and put markers every second. So that may be t equal to 0, t equal to 1, t equal to 2, and so on. So time is measured as a parameter along the motion of the particle. It is not explicitly shown. But you can sort of tell the particles moving slowly or rapidly by looking at the spacing between these tick marks. For example, here in 1 second, it went from here to here. Here in 1 second, it seems to have gone much further, so probably it's traveling faster. But if you want to describe this particle, what's the kinematics? You can pick a point and say, I am at the point xy. So when you go to 2 dimensions, you need a pair of numbers. Instead of x, you need x and y. But what we will find is it's more convenient to lump these 2 numbers into a single entity, which is called a vector. So that's what we're going to talk about a little bit, talk a little bit about vectors. Now, you guys have also seen vectors, I'm pretty sure, but it is worth going over some properties, and some may be new and some may be old. So the simplest context in which one can motivate a vector and also motivate the rules for dealing with vectors is when you look at real space, I mean, just coordinates x and y, and let's imagine that I went on a camping trip, and on the first day, here is where I was. Then I tell you, I went for 5 kilometers on the second day, and another 5 kilometers on the third day. Then I ask you, where am I? How far am I from camp? You realize that you cannot answer that. You cannot answer that even if I promise to move only along the x-axis. Because I think I don't want to pose this as a question, because I think the answer is fairly obvious to everybody. It's not enough to say I went 5 kilometers. I got to tell you whether I went to the right or whether I went to the left. So I could be 10 kilometers from home, I could be 0 kilometers from home, or I could be minus 10 if I'd gone 2 steps to the left. But you can deal with this by saying not just 5 kilometers, but plus or minus 5 kilometers. If you give a sign on top of the number, that takes care of all ambiguity in 1 dimension. So a signed number is adequate to keep track of my motion. But you know, in 2D, the options are not just left and right or north and south, but infinity of possible directions in which I could go those 5 kilometers. So what I could do on the first day is to come here. On the second day could be to go there. These 2 guys are 5 kilometers long. For that purpose, to describe that displacement, we use a vector. This is called a vector. I'm going to give it a name A. It starts from the origin and goes to this point. That is a description of what I did on the first day. And the second day, I did this, and that is the description of what I did on the second day. In fact, proper way to draw a vector is to draw an arrow. It's got a beginning, and it's got an end. So this is the reason behind saying a vector has a magnitude and a direction. Well, magnitude is how long this guy is, and direction is at what angle it is. So this is A and this is B. And now you realize that, oh, by the way, when you draw a vector like A, you're supposed to put a little arrow on top. If you don't put an arrow on top, it means you're talking about just a number A, which could be positive or negative or complex, but it's just an ordinary number. If you want to talk about an arrow of any kind, you've got to put a little arrow on top of it. In a textbook, they use boldface letters. In classroom, you use this symbol. Now, if this is A and this is B, it's a very natural quantity that you can call A plus B. If you want to call something as A plus B, it means that I did A and then I did B, but if I want to do it all in one shot, what is the equivalent step I should take? It's obvious that the bottom line of my 2-day trip is this object, C, and we will call that A plus B. It does represent the sum in the sense that if I gave you $4, then I gave you $5, I gave you effectively 9. Here we are not talking about a single number, but a displacement in the plane, and C indeed represents an effective displacement. This is the rule for adding vectors, and it has its origin in this simple example. Okay, so rule for adding the two vectors is you draw the first one, and at the end of that first one, you begin the second one, and the sum starts at the beginning of the first and ends at the end of the second. Okay, so that tells you how to add two vectors and get a sum. You can verify in this simple example that A plus B is the same as B plus A. B plus A would be first draw B, and from there you draw A, and you will end up at the same point. So you say this is a commutative law. It doesn't matter the sequence in which you add the two vectors. We know that's true for ordinary numbers, right? 3 plus 4 and 4 plus 3 are same. It's also true for vectors. But the law of composition is not always commutative. There are certain occasions in which you first do A and then you do B. That's not the same as first doing B and then doing A. We'll come to that later. Right now, this is the simple law. All right. Next thing I want to do is to define a vector that plays the role of the number 0. The number 0 has a property. When you add it to any number, it doesn't make a difference. So I want a vector that I want to call the 0 vector, and it should have the property that when I add it to anybody, I get the same vector. So you can guess who the 0 vector is. 0 vector is a vector of no length. I cannot, if this is A, I'm going to draw a vector here. I cannot show you the 0 vector. The minute you can see it, I'm doing something wrong, right? If you can see it, it's wrong because it's not supposed to have any length. But it has a property that when you add it to anything, you get the same vector. So that vector is called the null vector. How about this guy? I draw A, then I draw another A. This is A plus A. Now you have to agree that if there's any vector that deserves to be called 2A, it is this guy, right? This is A plus A. So we're going to call it 2A. The beauty of that is now we have discovered a notion of what it means to multiply a vector by a number. If you multiply it by 2, you get a vector 2 times as long. But then you're able to generalize that and say, if you multiply it by 2.6, I mean a vector 2.6 as long as A. So multiplying vector by a number means stretch it by the factor. Then I want to think of a vector that I can call minus A. What do I expect of minus A? I expect that if I add minus A to A, I should get the guy who plays the role of 0 in this world, which is the vector of no length. It's very clear that if you want to take A and ask what should I add to A, so I get the null vector, it's clear that you want to add a vector that looks like that, because then if you go from the start of this to the finish of that, you end up at the same point and you get this invisible 0 vector. So the minus vector that's the same vector flipped over to point the opposite way. So that's like minus 1 times a vector. Once you got that, you can do minus 7 times a vector or minus pi times a vector. Just take the vector, multiply it by pi, and flip it over. That's minus pi times a vector. This is how you get the rules for adding a vector to another vector, then taking a vector and multiplying it by some constant. Then, of course, you can do more complicated things. You can take this vector, multiply it by one number, take that vector, multiply another number, add the two of them. We know what all those operations mean now. But you don't have to memorize all this. The only rule is do what comes naturally, do what you would normally do with ordinary numbers, and this seems to work for vectors. But you should know what multiplying vector by a number means. All right, so this is the notion of what vectors are. Now we're going to come to some important concept, which is the following. You go back to the same xy plane. Here is some vector A. I'm going to introduce two very special vectors. They are called the unit vectors, and this guy is I, that is j. If I had a third axis, I would draw a k, but we don't need that. So I and j are vectors of length 1 pointing along x and y. The claim is I can write any vector you give me as a rescaled I plus a rescaled j. There's nothing you can throw at me that I cannot handle with some multiple of I and some multiple of j. Now, it's intuitively clear, but I will just prove it beyond any doubt. Here is the vector A. It is clear that that vector is the sum of that vector and that vector by the rules of vector addition, right? Because that plus that is equal to the A. But how about this part? This part being parallel to I has to be a multiple of I. We know that because you can stretch I by whatever factor you like. So whatever number it takes, Ax times I is this part. This part being parallel to j has to be some multiple of j. I'm going to call it Ay. Therefore, the vector A that you gave me, I have managed to write as I times Ax plus j times Ay. So you can ask yourself, if you gave me a particular vector, what do I use for Ax and Ay? Well, you can see from trigonometry that if this angle was theta here, and that the length of the vector I'm going to call by A. A is the length of A. If you drop the arrow, it's the usual convention is you're talking about the length of the vector A. First of all, it's clear from the Pythagoras theorem that A is square root of Ax squared plus Ay squared. And the angle theta that it makes with the x-axis satisfies the condition tan theta is Ay over Ax. So what this means, now here's the main point. If you give me a pair of numbers Ax and Ay, that's as good as giving me this arrow, because I can find the length of the arrow by Pythagoras theorem, and I can find the orientation of the arrow by saying the angle theta satisfies tan theta is Ay over Ax. So you have the option of either working with the two components of A or with the arrow. Now, in practice, most of the time we work with these two numbers, Ax and Ay. If you're describing a particle with location r, the vector we use typically to locate a particle, r, then r is just I times x plus j times y, because you all know that's x and that's y. Now, I've not given you any other example besides the displacement vector, but at the moment, we'll define a vector to be any object which looks like some multiple of I plus some multiple of j. So suppose I tell you to add two vectors, A and B, equal to C, and I say what's the result of adding A and B? You got two options. You can draw the arrow corresponding to A, then you make an arrow corresponding to B, you lay it on the edge of this one, then add them as shown here. But you can also do something without drawing any pictures. That would come by saying I'm taking I times AX plus J times AY plus I times BX plus J times BY, and I'm trying to add all these guys. But then I combine I times AX with I times BX, because that's a vector parallel to I with the length AX. That's a vector parallel to I with length BX. It's clear if I add them, I'll get a vector parallel to I with length AX plus BX. Then J equals AY plus BY. I have to be a little careful when I said add the lengths. I'm assuming all the components are positive. If the AX and AY, some are positive, some are negative. This is the way by which we have learned we should combine multiples of I. When I give you multiple of I and another multiple of I, their sum has got as its coefficient the sum of the two coefficients. This says when you add two vectors, you just add the components. So that if this vector is called I times Cx plus J times Cy, then it's worth knowing that Cx is Ax plus Bx and Cy is Ay plus By. So most of the time when we deal with vectors, we don't draw these arrows anymore. We just keep a pair of numbers. And if you give me another vector, that's another pair of numbers. And if you say add the vectors, I will just add the x to the x and the y to the y, and I'm keeping track of what the sum is. A very important result is that if two vectors are equal, if A equals B, the only way it can happen is if separately Ax is equal to Bx and Ay is equal to By. That's the very important difference. You cannot have two vectors equal with exactly the same x component, exactly the same y component. That's pretty obvious. If two arrows are equal, you cannot be longer in the x direction and correspondingly shorter in the y direction. Everything has to completely match. So vector equation A equals B is actually a shorthand for two equations. The x parts match and the y parts match. Okay, now when you work with components, Ax and Ay, if I didn't mention it, they are the components of the vector. So you can do all your bookkeeping in terms of Ax and Ay, but you got to be aware of one fact. If I just come and say to you, here's a vector whose components are 3 and 5. Can you draw the vector for me? Can you draw it or not? Does anybody have a view? Yes? No? Yes?
No.
Pardon me?
You don't know the directions?
Yeah, if you immediately said, well, if the vector is 3, 4, then the vector looks like this, you're making the assumption that I am writing the vector in terms of I and j. Now, you see, I and j is very natural direction. For most of us, gravity acts this way, defines a vertical direction very naturally. Then the blackboard is oriented this way. It's very natural to call that x and call that y and line up our axes. But do you agree that there is no reason why somebody else couldn't come along and say, you know what, I want to use a different set of axes. Those directions are more natural for me. In fact, just because the world is round, you can already see if this is the earth, to somebody, that's a natural direction. If you go to another neighboring country, that's what they think is naturally x and y. So there's no reason why x and y are nailed in absolute space. It's very important that x and y are human constructs and we're not wedded to any of them. Quite often it's natural to pick x and y in a certain way. If you're studying a projectile near the earth, it makes sense to pick the horizontal as x and vertical as y. But mathematically, you don't have to. So a very important point that comes up is the following. What if somebody comes along and has got a new axis, and here is a unit vector I prime, that's unit vector j prime, and here is this vector A. And the angle between my axis, let's say, and your axis is some angle phi. The same vector A can be written either in terms of I and j or in terms of I prime and j prime. So let's take a minute to just play this game of asking, how are the components of A in the new rotated coordinate system related to the components in the old coordinate system? This is a simple problem, but I just want to do it so you get used to working with vectors. So the point is, the arrow A, somebody has chosen to write in terms of I prime and j prime as ax prime and ay prime. You guys follow that? I prime and j prime are now rotated unit vectors. And somebody wants to think in terms of those. In other words, the person wants to ask, how much I prime and how much j prime do I need to build up the vector A? That person will get a definite answer. You're asking, how much I and how much j do I need to build the same object? So the same entity written in two different ways. So she's got a pair of numbers and you got a pair of numbers. The new numbers are called the prime numbers, and you want to write them in terms of yours. Well, for that, what do you need? You need to know what I prime is in terms of I and j. So let's draw a little picture on the side here. This is I prime. It's got length 1. It's at an angle phi. So I'm going to write something, and I'll wait till you guys tell me you're comfortable with this. I prime is I cosine phi plus j sine phi. There should not be anybody in this room who is mystified by this statement. This vector I prime has got a horizontal part, which is its length, which is 1 times cosine phi, and a vertical part, which is 1 times sine phi. This kind of trigonometry you should know all the time. Okay, it's not something you're going to go back and remember. Is it opposite side? Is it adjacent side? You got to know that really well. So you got to be very used to the notion of taking a vector in some oblique direction, writing it in terms of I and j. How about j prime? J prime is pointing in that direction. It's at an angle phi. So j prime will be minus I sine phi plus j cosine phi. If it's not obvious, I think this is the kind of thing you should fill in the blanks when you go home. Leave a line there and think about it and fill in the blanks later. Very important to know, if these two axes are at angle phi, those two axes are also at angle phi. That's the result you use all the time in mechanics. So once you do that, I think it's fairly clear that it has got a y component that's given by cosine, an x component that's given by sine phi, but the x component is negative, because this vector has a little bit of negative I in it. Now here's what I say you should do, and this is the kind of thing I don't want to do in classroom. It takes time, and I'm probably going to screw up. So imagine taking I prime and j prime and stick them here and here. Do this in your head and ask, what can I possibly get? I prime and j prime have been banished. Everywhere they're replaced by I and j. So you can now collect the whole expression as something something I plus something something j. And what you will get for I will be ax cosine phi minus ay sine phi. Then here you will get ay cosine phi plus ax sine phi. This is the only part I don't want to do explicitly. I'm just saying take this and put it there and combine I and j. But this is the same vector we are calling I times ax plus j times ay. And I've told you if two vectors are equal, the components must match. I may then, I'm sorry, I'm making a mistake here. This should be primed. By the way, when you guys do this, did anybody notice it's a prime? Yeah, so if you noticed it, you got to stop. You cannot let me write anything that's incorrect. So you got to follow it in some detail. I know you couldn't do the details, but you should at least know there is I prime and j prime that have been replaced by I and j, but ax prime and ay prime will continue to be the coefficients. So if I make a comparison, I find ax is equal to ax prime cosine phi minus ay prime sine phi, and ay is equal to minus ax prime sine phi plus ay prime cosine phi. So what's the purpose of the exercise? The purpose of the exercise is to make the following precise remark. You can pick your unit vectors, or what are called basis vectors, any way you like. Pick any two perpendicular directions which may be related to the ones I picked by an angle phi. Then the same entity, the same arrow, which has an existence of its own independent of axes, can be described by you and me using different numbers. But there's a precise connection between the numbers you use, the numbers I use. Your numbers with the prime on it are related to mine by this relation. Now you can ask the opposite question. How do I get your numbers in terms of my numbers? So what should I do? If I want to invert the relation, anybody have an idea what I should do now? No one has a clue on how I can go back from these to that? Let me take a second to ask. Do you have any idea what you should do? Okay, maybe you are, yes?
Maybe you can add up those two expressions and rearrange them using algebra.
Yep.
Can you just use those same expressions, but use a prime or a prime x for every a x and vice versa, and then just use a negative phi?
Negative of phi, yes, okay. All right, so his idea was the formula written for the opposite one will have the opposite angle. Replace this phi by minus of that. Now that turns out to be the correct answer, but I want you guys to think about why it was difficult to do it another way, which is more pedestrian. I mean, if I told you 3x plus 2y is 9 and 4x plus 6y is 6, you certainly know how to solve for x and y, right? This is something you've seen in your high school. You've got to juggle the two equations, multiply that by 4, multiply that by 3, add and subtract, and so on. Why is it when you saw this, you didn't realize it's the same problem? But it's the same problem. This phi is an angle. Sine and cosine are definite numbers. If I pick an angle of 60 degrees, these are some numbers like half and root 3 over 2. Then I'm trying to write these two unknowns in terms of these two knowns, and you can solve for them. Here, though, what you will multiply by would be sine phi's and cosine phi, so you can eliminate. For example, if you multiply this by sine phi and multiply this by cosine phi and add them, the ax prime will drop out. So that's the kind of thing you should do. Maybe you should, I will add this on as a problem you should do in the homework. But do you realize that this is a pair of simultaneous equations in which you can solve for these two unknowns, if you like, in terms of these two knowns and these coefficients, which are like these numbers 3, 2, 4, and 6. You can do that, but we like to get the answer the way this gentleman described it, because we like to get an answer more readily than by doing the mundane work. And the idea that he had was, if you go from me to you with a clockwise rotation, you go from you to me by counterclockwise rotation. Therefore, if my angle, if I go by phi to you, then you must go by minus phi to come to me. That's correct. So you will find then the result is ax cosine phi plus ay sine phi. I'm using the fact that when you take a cosine and change the angle inside the cosine, it doesn't care. Whereas if you go to the sine and change the angle inside the sine, it becomes minus sine. In other words, sine of minus theta is minus sine theta, and cosine of minus theta is cosine theta. These, by the way, is another property I expect people to know in this course. You cannot say, I've never heard of it, or I don't know where it came from. You should think about why that is true. Okay, so if you do that, you will find then this result. Okay, so there is a way to go from the unprimed coordinates, the prime coordinate, by rotating your axis and actually calculating the components. Now, here is a very important message, which is the following. When you go from one set of axes to another set of axes, the numbers change. The components of the vector are not the same. You might think it's all along x, and somebody can tell me it's all along my new y-axis. So the components of the vector are not invariant. They depend on who is looking at the vector. But there's one quantity that's going to come out the same no matter who is looking at the vector. Anybody have a guess on? Yes? The length of the vector is the length of the vector. Perhaps it's clear to you that no matter how your axes are oriented, when you ask how long is this arrow, you're going to get the same answer. And that means ax squared plus ay squared is ax prime squared plus ay prime squared. And that's a property of this expression. You can square this guy and add it to the square of this guy, and you will find, using the magics of trigonometry, that this is true. Now, I'm going over these points because they're very, very important. When we do relativity, we'll be dealing with vectors in space-time, and there we'll find that different observers disagree on what is this and what is that, but they will agree on certain things. Yes?
So is there a minus in front of both the ay and ay prime in front of the ax prime side?
Here?
No, on the second part?
Here?
Is there a minus in front of both of them? Should there?
This has a minus, and that doesn't have a minus.
But on the other side, ay?
Oh, here?
Yeah, that's
No, here both are plus, but this one has a minus.
was there a minus sign before?
Oh, I'm so sorry. Yes, that is correct. Thank you. That's right, the minus is only there. Very good. So certain things are called invariants. This is an example of an invariant. By the way, I want to conclude with one important point. We learned that a vector is a quantity that has a magnitude and a direction. But actually, the view of vectors we take nowadays is that a vector is a pair of numbers, are associated with a pair of numbers, which under rotation of axes transform like this. Anything that transforms this way is called a vector. All right, so now I want to ask the following question. Can I manufacture new vectors? We got one vector, which is r. How about more vectors, more position vectors? So I want to look at that. So that turns out to be a very nice way to produce vectors given one vector, the position vector. And that's the following. Let's take a particle that is moving in the xy plane so that at one instant, so let me change this graph. It's here. Oh, this is bad. Let's see. It's moving like this. So I'm here now. A little later, I am there. That's what I meant. So this is called r. This is called delta r. This is called r plus delta r. So the particle is moving along this arc. Initially, its location as a function of time is equal to I times x of t plus j times y of t. If you wait a short amount of time, it goes to the new location, which I'm going to call r of t plus delta t. What can that be? It can be x of t plus some change in x plus j times y of t plus a change in y. That we recognize to be r at time t plus everything else, which is I times delta x plus j times delta y. I'm going to call this guy a tiny vector delta r. In other words, when you move on a line, you wait a small time delta t, you move by an amount delta x. When you move in the plane, your change is itself a vector. You start with the vector, you change by this vector delta r, it gives you the new location. Delta r has got two components. It's got a change in x and it's got a change in y. Therefore, we will define what's called the velocity vector, which is, if you want, the limit as delta t goes to 0 of delta r over delta t. And you can see that is going to be I times dx dt plus j times dy dt. So you can actually take derivatives of a vector with time. And that's also a vector. Why is the derivative of a vector also a vector? Because the difference in the vector between two times is this vector. Dividing by delta t is like multiplying by 1 over delta t. But I know when I multiply a vector by a number, I get a vector in the same direction. So what this really means is that if you take the limit as delta t goes to 0, I cannot draw it that well, but imagine bringing the second point closer and closer to the first one. Delta r is getting very small, delta t is very, very small, but by the miracle of calculus, the ratio will approach a definite limit. That limit will be some arrow you can call the velocity at that time, and it will always be tangent to the curve, because tangent is pointing towards the direction you're headed at that instant. So if I gave you the location of a particle as a function of time, you can find the velocity by taking derivatives. For example, if I say a particle's location is I times t squared plus j times 9t cubed, for every value of time, you can put the numbers in, and you can find the velocity by just taking derivatives. Derivative of this guy will be 2t times I plus what? 27t squared times j. So rule for taking derivatives, if you want to do just mindless application of calculus, you can do it. I and j are constant. Ignore them when you take derivatives. X and y depend on time. Just take the derivatives, and that's the velocity vector. And you can take a derivative of the derivative, and you can get the acceleration vector. Will be d2r over dt squared, and you can also write it as dv dt. Okay, anybody have a question with what I've done now or what we're doing here? Let me summarize what I'm saying. Particles moving in a plane. At every instant, it's got a location given by the vector r. R itself is contained in a pair of numbers, x and y, and they vary with time. So when you vary time a little bit and ask how does r change, and you take the quotient of delta r to delta t, you get the velocity vector. Mathematically, it's done by taking the expression for r and differentiating everything in sight that can be differentiated with respect to t. So even though we started with a single vector, which is the position vector, we are now finding out that its derivative has to be a vector, and the derivative of the derivative is also a vector. Again, when you learn relativity, you will find out there's one vector that's staring at you. I'll come to what that is. That's the analog of the position vector. But more and more vectors can be manufactured by taking derivatives. Okay, so now I want to do one concrete problem where you will see how to use these derivatives. I'm going to write a particular case of r of t and take derivatives, and we'll get a feeling for what's going on. The problem I have in mind looks like this. R of t is going to be a fixed number r times I times cosine omega t plus j times sine omega t. This omega is a new creature. You don't know what it is right now. But I'm going to just put that in. And omega times t is some number, and it's the cosine of the number times I plus sine of the number times j times r. So what is going on as a function of time? What's this particle doing? First thing you can tell is that if you find the length of this vector, you'll find the square of the x and the square of the y, but since sine square plus cosine square is 1, you'll find this vector as a fixed length r. That means it can only be rattling around in a circle of radius r. And in fact, what the guy is doing looks like this. At any given time t, draw an angle omega t and a radius r, and that's where your particle is. You see that? Because the x component of this one is r cosine omega t, and the y part is r sine omega t. As omega is a fixed number, as t increases, this angle increases and the particle goes round and round. So we're describing the motion of a particle on a circle. Now let's understand what omega is. Let's get a feeling for omega. As time increases, the angle increases, and we can ask, how long does it take for the particle to come back to the starting point? Suppose the starting point was here. So as I increase little t, omega t will increase, and I want to come back to where I start. So you've got to ask yourself, let the time it takes to do a full circle, that's the time period, do a full circle. Then what can you say about omega t? What should be the value of omega t? Very good. So you can say it's 360 degrees, that's fine. But we like to measure angle in radians. Now, how many people know about radians? Okay, for those who have not seen a radian, it's just another way to measure angle, with the understanding that a full circle, which we used to think is 360 degrees, is equal to 2 pi radians. 2 pi is roughly 6. So radian is roughly 60 degrees. It's 58 and fraction. Why do we like to measure angle in that peculiar way? You will see the advantages of that later. But we'll adopt the convention that we'll measure angle in a radian. So that a half circle, instead of calling it 180 degrees, you will call it as pi. And a quarter circle, instead of 90, you will call it pi over 2, and 45 is pi over 4, and so on. But it's good to know certain famous angles. This is pi over 2, this is pi, this is 3 pi over 2, and this is back to 2 pi. Therefore, omega t equal to 2 pi tells you that omega is 2 pi divided by the time it takes to complete a revolution. And 1 over the time period is what we call the frequency, so you can write it as f is just the usual frequency. 60 hertz means you do 60 revolutions per second. All right, so how fast is this particle moving? It's going around a circle. The angle is increasing at a steady rate, so we know it's going at a steady speed. I'm asking, what's the tangential speed as it moves along the circle? Yes? How do you reach that conclusion?
The tangential speed is proportional to the radians.
I agree, but I want the speed in meters per second, and omega will be in radians per second. Yes?
Omega r,
And how did you get that?
because radians per second times the radius of the circle gives you the speed,
Okay, but
whatever unit.
that's correct. But let me deduce that in another way. Your answer is completely correct. It is omega r. But I want to say how you get it. One way is to say, if I do a full revolution, I think of the speed as the distance over time. I'm going to go 1 full revolution. Distance I travel is 2 pi r. But 2 pi over t was identified as omega. So the tangential velocity at any point is equal to omega times r. That's a useful quantity to know. So now you can take this velocity and you can take this r. Now let me find v of t. V of t is obtained by taking derivative of this expression. I think you guys know enough calculus for me to write is equal to r times I times minus omega sine omega t plus j times omega cosine omega t. That is the velocity of this guy, and I invite you to try this formula whenever you want. Pick a time. Let's say if I go a quarter of a circle, I expect to be moving to the left. quarter of a circle means omega t is pi over 2. Cosine of pi over 2 is 0 because cosine 90 is 0. Sine of pi over 2 is 1. And I get a speed of omega r in the negative I direction. Since omega r was the speed, that's indeed the correct answer. And you can satisfy yourself at various times it's going like this. So let's sneak in one more derivative here, which is to take the derivative of the derivative, and that's a very important result. If you do that, let's take one more derivative. Let's try to do part of it in the head so I can just write down the answer. If you take one more derivative, the sine is going to become a cosine and yield another omega. This cosine is going to become a minus sine and give me another omega. If you do that, you will find the whole answer is equal to minus omega squared times just the vector r itself. That's a very interesting result. It tells you when a particle moves in a circle, it has an acceleration in the negative r direction, namely directed towards the center. What's the magnitude of that acceleration? I write it without an arrow here. That's equal to omega squared times the magnitude of this vector, which is just r. But now I can also write it as v squared over r. So here, ready? This is a very important formula. I don't know how many kids, generation after generation, get in trouble because they do not remember the following fact. So I'm going to say it once more with feeling. When a particle moves in a circle, it has an acceleration towards the center of this size, v squared over r. Very simple. It comes from the fact that velocity is a vector, and you can change your velocity vector by changing your direction. This particle is constantly changing its direction, but it therefore has an acceleration, and the acceleration we have shown here is pointing towards the center, and the size of that is v squared over r. So for example, if a car is going on a racetrack and you're seeing it from the top, if the gas pedal says 60 miles per hour speedometer, you might say it's not accelerating. But that's the layperson's view. But if it's going on a circle, you will say from now on that it indeed has an acceleration, even though no one's stepping on the accelerator, of amount v squared over r. So that's a very important thing. That's the part, that's what you're learning in this course. The fact that when you step on your gas, you accelerate, everybody knows. The fact that when you go in a circle, you accelerate is what we're learning here, and it's coming from the fact the velocity is a vector, and its change can be due to change in the magnitude or change in direction. This is a problem where the magnitude of velocity was nailed down and fixed at omega r, but the direction is constantly changing. Okay, so I'm going to now do a second class of problems. We will return to this issue later. By the way, one thing I should mention to you. Suppose the particle is not moving in a circle but does this. Let's take a circle and just keep a quarter of the circle. During this part, when you're doing a quarter of a circle, this is supposed to be a quarter of a circle, you have the same acceleration directed towards the center. In other words, you don't have to be moving actually in a circle to have the acceleration. At any instant, your motion, if it follows any curve, locally can be approximated as being part of some circle, right? You can take circles of different size and place them against your trajectory, see which one fits. That's the r. v squared over r is the acceleration directed towards the center of that circle. Okay. One miscellaneous result, which we don't use very much now, but which I should mention to you, is the following. Suppose this is the ground with some origin here. That's a plane with some origin here. And in the plane, there is some other object. What's the location of the object? Let us say P for plane, G for ground, O for object. I think it's clear the position of the object with respect to the ground, this vector, is the same as the position of the object with respect to the plane plus position of the plane with respect to the ground. You agree? Okay. This is the picture here. Now you can start taking derivatives of this with respect to time, and that will say the velocity of the object with respect to the ground, the velocity of the object with respect to the plane, velocity of the plane with respect to the ground. That means if you're going in a plane and you throw something up in the air, it seems to be going up and down to you. But if I see you through the glass, the object is going on some trajectory which has got both up and down and horizontal motion. And this is the rule for adding velocities. So when you have a velocity in the moving plane frame and you want to find the velocity on the ground, you should add to every object in the plane the velocity of the plane with respect to the ground. That's intuitively clear. You use it all the time, but maybe along one dimension, but this is the way to do it in 2 dimensions. There may be some simple problem involving this in the problem assigned, so I'm just going over this. Okay, the problem we want to do today, whole family of problems, looks like this. I want to consider a particle which has definite acceleration a constant one, but a is now a vector. The question I have is, what is its location at all future times? I think you can tell by analogy with what I did in one dimension that the position of that object at any time t is going to be the initial position plus velocity times t plus 1/2 at squared. Everything is the same as in 1D, except everybody is a vector now. Initial position is a pair of numbers. Initial velocity is a pair of numbers. Once you know those, you can find the position of the object at all future times. So let's take one simple example. So there is somebody in a car and decided to fly off. And we want to know, as you can tell, our concern is where does the car hit the ground? When does the car hit the ground? That's the problem in 2 dimensions. So how do we solve this problem? We pick our origin to be this point here. Let the height of the building be h. Car is traveling with some initial speed v0 in the horizontal direction. This equation is a pair of equations, one along x and one along y, right? For the x part, I'm going to write x is equal to x0 plus v0t. And x0 I'm going to be choose to 0 by choice of my origin being here. The x coordinate of the car is the 0 because this is my origin. How about the y coordinate? The equation for the y coordinate is the height of the building. The velocity has no vertical component, so there is no vy, but it has an acceleration of minus g. So this is the fate of this person at any given time t. At t equal to 0, you have him right on top of this edge, and at all future times, x proceeds as if nothing happened, and then y you're falling. And if you want to know something like when do you hit the ground, I think it's fairly clear what you have to do. For example, if t star is the time you hit the ground, then t star satisfies the equation h minus 1/2 g t star squared is 0. You solve for the t star from this one, and you put it there, and that tells you where you land. I don't think I have to actually do that step. I'm assuming you can fill in the blanks, right? Solve this equation for t star, put it there, and that's where you land. Okay, that's one class of problems. So here's a second class. The second class is the most popular application of what I'm doing now. But I want you not to memorize every formula the book gives you for this problem. That's the problem of projectile motion. So projectile motion, you start here and you fire a projectile with some velocity v0 at some angle theta, and it's going to go up and it's going to come down. One question is, where is it going to land? Another question is, at what angle should you fire your projectile so it'll go the furthest? So you can find the equations, but you got to think a little bit before you solve everything. It's good to have an idea of what's coming. So imagine you got this monster cannon. You can fire things. It's got a fixed speed, v naught. And how do you want to aim it so you can be most effective, go as far as you can? Well, there are two schools of thought. Okay? One says aim at your enemy. Fire like this, then it lands on your foot, because assuming the cannon is at 0 height, the cannonball certainly comes out towards the enemy but has no time of flight. Other one says maximize the time of flight, and you point a cannon like this. So it goes up, stays in the air for a very long time, but it falls on your head. So we know the truth is somewhere between 0 and 90. A naive guess may be 45, but it turns out naive guess is actually correct. So I just want to show you how that comes out. But I don't want you to cram this formula. This is the kind of thing you should be able to deduce. So let's go back to the same thing I wrote earlier. X equals 0 plus, what's the horizontal velocity? Horizontal velocity is v0 cosine theta. So x is v0 cosine theta times t, and y is v0 sine theta times t minus 1/2 gt squared. Okay, so now we know everything about this particle. I told you, once you know the three parameters, r naught and v naught, you know everything about the future of the object. So let's ask, what's the range? Range is that distance. So what's the strategy for range? You see how long you are in the air, and the whole time you are in the air, you are traveling horizontally at the speed. So again, let t star be the time when you hit the ground. So you said 0 equals v0 sine theta minus 1/2 gt star times t star. I just pulled out a common t. So it says you are on the ground on two occasions. One is initially, but we are not interested in that. Well, if the time you're interested in is not 0, you're allowed to cancel it and get the time from here, and that time is t star equal to 2v0 sine theta over g. That's how long you're in the air. This says if you want to be in the air for a long time, maximize sine theta, so you may think it's 90 degrees is the best angle. But that's not the goal. Goal is to get the biggest range. So go back to x and put your value for t star, which is 2v0 sine theta over g, and that becomes v0 square over g times 2 sine theta cosine theta. Now if you go back to your trigonometry, you should find that is really the formula for sine 2 theta. That's another example where knowing the trig identity is very helpful. Okay, so this tells you exactly what you want. It says make sine 2 theta as big as you want, and that tells you 2 theta is going to be 90 and theta is going to be 45. But it's not from a naive guess that it's halfway between 0 and 90. It turns out to be the result of fairly complicated balance between the time of flight and the range. So some people memorize this. I would say don't do that, because after a while you won't have room in your head for anything. Just go back as often as possible to this formula and work your way from there. Now there's more variations, but it's always the same thing. Here's another variation. In my days, they would say, find out when you want an object to go through that point. And I tell you the muzzle velocity v naught, or I tell you at what angle I fire it, I want you to find the speed so it'll land here. So how do you do that problem? You do that problem by saying, suppose this actually happens at some time t. At that time t, the x coordinate must have a certain value. So I go to the x equation and demand that this be equal to the desired x value and find the time. I take the time and put it in the y equation and demand that the y I get agree with this y. If you do that, you will find there's one unknown, which is v naught, and you can solve for v naught. This is the most general problem you can have. Now in the textbook, of course, people make them interesting. Suddenly there's a mountain, and there's a physicist hiking on this mountain. See, you're already laughing. So this is not a very credible problem. We don't hike, and when we get stuck, we don't want food. We want our table of integrals, which is what we want somebody to send to us. So these problems are embellished in many ways to make you all feel involved. For example, instead of a stone dropping, nowadays there's a monkey that's falling down. So the people in life sciences feel, hey, we are represented in this subject. But all those creatures, which are very interesting, in the end, you are told, there's a horse inside a railway carriage, and you cannot see the horse, but the horse is moving. You can deduce it because the carriage is moving the other way. There's a picture of a horse, a picture of a carriage, all glossy stuff. Then it says, treat the horse as a point particle. See, that's what we learned in the old days. But nowadays, it's a horse, but in the end, if you're going to treat it as a point particle, it seems to me to be a real waste. If you're the godfather, right? You want to get the contract for Johnny Fontaine, you don't tell your consigliere, hey, Tom, put a point particle on Jack's bed, right? When you want a horse, use a horse. When you want a point particle, if you wake up and find a point particle on your bed, what's your reaction? So I think these extra pictures, sometimes they're helpful, sometimes they just make the book cost a lot more. There are problems where a horse must be treated, we'll see when we study rigid bodies. Even there, a horse is not really a rigid body unless it's been dead for a long time. But at least there, the fact it's not a point particle is important. So I think the reason books are bigger and bigger but still carry the same information is that examples are more and more interesting. Sometimes they serve a purpose, sometimes they're distracting. But I haven't written a book in this field, so I will not say anything more.